The 100-year gravity error, the gravitational constant we use for solar system navigation, is effectively useless at a galactic scale without a massive placeholder called dark matter. General relativity is mathematically sufficient for landing a rover on Mars, but it fails to predict the orbital velocity of galaxies by an order of magnitude. NASA JPL physicist Slava Turyshev just published a framework in April 2026, arguing that this discrepancy is not a mass problem, but a measurement resolution problem. If his analysis of the Great Disconnect holds, the fundamental law of gravity is missing a specific, high-frequency component that our instruments have simply been too blunt to detect. This measurement gap starts with the precise failure of the PPN parameter. The PPN Precision Wall. We measure gravity using the parameterized post-Newtonian parameter, or gamma, which dictates how much space curves per unit of mass. For Einstein's model to be the final word, gamma must equal exactly 1. Current tests from the Cassini mission confirm this to within 0.00002. However, Turyshev's new study suggests that a fifth force, specifically a long-range scalar field, would only manifest at a precision of 10 to the -9 or higher. We are not seeing a failure of Einstein. We are seeing the limits of our current sensor architecture. Moving beyond this resolution requires a new kind of laboratory located at the Sun's L1 point, the laser ranging solution. Turyshev's April 2026 paper outlines a mission using a constellation of small satellites equipped with optical atomic clocks and laser interferometers. By measuring the Shapiro delay, which is the time it takes for light to pass near the Sun's mass, the experiment can detect deviations with sub-picosecond accuracy. This is a purely mechanical hunt. By comparing the laser phase between two spacecraft, we can isolate gravitational signatures that cannot be explained by standard baryonic mass. This would effectively transform the solar system into a massive detector for a fifth force that acts as a corrective term to gravity over astronomical distances. But critics argue that local noise is still the biggest hurdle for this mission. The solar noise constraint. The skeptics have a valid point regarding non-gravitational acceleration. Solar radiation pressure and the solar wind produce forces that are orders of magnitude larger than the fifth force Turyshev is hunting. To extract a clean signal, the mission requires drag-free control systems, where a proof mass floats inside the hull, untouched by the spacecraft itself. If the microthrusters cannot compensate for solar photon pressure in real time to keep that proof mass centered, the entire dataset is functionally noise. The signal under the noise. The hunt for a fifth force represents a shift from searching for invisible dark matter to refining our understanding of how space-time reacts to mass at high precision. Turyshev's PPN analysis suggests that the dark matter mystery might actually be a hardware limitation in our current gravitational sensors. If we find that gamma deviates at the 9th decimal place, the standard model of cosmology collapses, and we trade the search for theoretical particles for a new set of scalar tensor equations. For engineers and mission planners, this means the next generation of deep space probes will not just be messengers, but active sensors for the fabric of the vacuum itself. The implications reach from orbital mechanics to the way we calculate long-range trajectory corrections. Watch for the mission design review of the Deep Space Gravity probe in late 2026 to see if the noise shielding specs meet the precision threshold required to prove Einstein was only partially right. Subscribe for more